So I have a solution of tin chloride, which is usually pretty insoluble, and I have copper, okay, hopefully, and I have my tin, my pretty metal tin here, okay? And as I have done previously, we showed that copper placed in tin chloride is non-spontaneous. It's sitting in tin chloride, and right now I can see that there is no, okay, there is absolutely no tin being plated here. All right, so it's sitting in tin chloride. Now I showed you another demonstration previously to this video where we put in a blue solution or a copper solution, I put tin, and tin does plate, okay, or the copper does plate on the tin, but this does not. The tin plus 2 has a negative reduction potential. Therefore, it's negative 0.14 volts is needed for it to plate onto this electrode. So we're going to force it to happen. And what I have below right here is a DC source. And in this DC source, I'm going to add a voltage and an amperage. We should know the difference. Okay, our voltage, and here's our voltmeter here. That's what the DC current is going to give us, the energy per charge. And then I have the amperage here, and that's going to be the flow of charge. It actually exists. So let's turn this on without my hands touching these electrodes, and let's see what's going to happen here. So I'm going to first understand where the leads have to go. So I have the place that I want reduction to occur, the cathode. I want the tin plus 2 that's in solution to go here. So this must be the cathode. So this black lead goes to the anode part of the battery, or the DC source. So this anode connects to the cathode. And because the black lead connects to the anode part of the battery, which is below this red here, all right, this is a negatively charged cathode. This red lead goes to the cathode part of the battery, and that is positive, so it makes this charge here positive. You cut these leads right here, electrolytic cell has no charge. It's creating the potential difference again is the DC source. All right, so I'm going to turn this on, and we should have a flow of charge from the anode to the cathode. And at this point right here, tin plus 2 in solution should be getting reduced onto the copper, which didn't occur naturally. And over here at the anode of the electrolytic cell, we're forcing charge back to the battery, and tin 0 becomes tin plus 2, so we're replacing the tin ions. So let's just stop talking about it. Let me turn this on. I just don't want these metals touching because charge will flow from the path of least resistance. So let's turn this on. So we're hoping to see the tin get smaller as it gets oxidized into ions, and this electrode to get bigger, woo, a little charge there, all right, as it tin plus 2 reduces on here. Let's turn this on. Looks like it's on a little bit because I got a little volt charge here. So we turn this on. Okay, and you can see from the top here there's an amperage flowing. That means there's some electrons flowing, and I have some sort of a voltage, a potential difference. Okay, and probably get some up close and personal shots here, but we definitely have some bubbling going on. And because I'm doing this in an aqueous environment, I can't help but to oxidize and reduce water. Okay, now as we let this go, what's happening with water? Well, think about this for a second. Water is polar. These pair of electrons are closer to the water. So I'm dangling in water protons, right? These are essentially just protons. I mean, there's a pair here and a pair here and a pair here. But these are protons. So think about this. The electrode that has a readily available number of what? Electrons is the cathode or the anode of electrolytic cell. Who's got the electrons? Well, the anode is pumping them, and this cathode has electrons, has charge. So at the cathode of the electrolytic cell, a side reaction is the water, or the H's that are essentially protons, will what? Absorb those electrons and become H2 gas and 2 hydroxides. So 2 water molecules plus how many electrons? Plus 2 electrons make H2 gas and 2 hydroxides. So the fizzing occurring here on the cathode electrolytic cell is water getting reduced. And over here you're going to have some oxygen being made. But we can clearly see that there's a buildup of something on the copper now, can't we? Okay? That's hard to see, but the tin is also getting a little depleted. All right, so let's stop this so I don't shock myself and take out what we have here. Now, it's not pretty, not the best way you want to plate, but you can clearly see that we definitely put some tin on here. Now, if I was to have a molten solution like we do in industry, it would be a pretty nice lustery, silvery kind of metal here. Okay, so clearly we forced plating that normally didn't occur. Okay, all right, so we forced a redox reaction to occur by electrolysis. Now, the interesting thing here is that I can predict and calculate how many grams of tin will plate, and that's an important procedure using something called Faraday's constant. We're going to do that right now.